a bandpass channel that goes from 100 to 200 hertz. The signal constellation that looks like this, no matter what those two basis functions I chose, even if they weren't cosine plus and minus, would be far apart. So that hopefully separates my messages. Yes, sir? I don't need to. You're correct. For this particular example, I could have done it with 1, which is what we did with the 150 hertz earlier. But this is actually what's done in satellite TV. You basically have a two-dimensional modulation that's used for BPSK like this. So often when you see BPSK, it's something, it's formulated in terms of in-phase and quadrature components, which we'll talk about in Chapter 2. But you're right, I have not used the minimum number of basis functions that I could have used for two signals. Obviously, when I only have two messages, I could always get away with one dimension and just send plus or minus on that. And we're actually going to come a little bit later in the class to a procedure that allows you to look at a set of basis functions and say, do I have too many basis functions for the number of messages that I'm going to transmit? And it's called Gram-Schmidt orthonormalization procedure. So you're right. Why did I choose this? It's not a very good choice in terms of fundamental principles. There may be other reasons for doing that in the transmission system that aren't apparent here. Another example that we could look at with those same constellation points. Let me draw that again. I had a phi 1 and a phi 2, and this was, let's say, x0, and this was x1. I could create almost any two basis functions that I like. I could actually even think of them. Let's say we had phi of f, the Fourier transform frequency. I could have phi 1 here and phi 2 there, different frequencies. Now clearly, if I look at these two functions and say, are they orthogonal? We're going to see a theorem a little bit later called the Parsifal's theorem that basically says if we integrate the product of two functions in the time domain, we can take their Fourier transforms and integrate them instead in the frequency domain, and the value of the integral is the same. Clearly, these two basis functions don't overlap in frequency, so if I take one times the other, I'm going to get 0. If I take one times itself, I'm going to get some constant value, and I'll set the level of the function so that I get 1 to make it a normalized basis. That's not the same basis as plus or minus some carrier frequency. But if I had two basis functions that look like this, and I could somehow extract the components on each of those basis functions, which you're going to see later is called demodulation, this constellation is still a good one to use. This is sometimes called frequency division multiplexing in modulation, because I have two basis functions using different frequencies. There's a lot of different ways to get orthonormal basis functions. Yes, sir? Yes. Yeah, these things would basically go to infinity because they'd be sinc functions. And we're going to, in Chapter 3, we'll actually deal with that effect. We just have to make sure that they go to 0 at the right places so that essentially if you sample in just the right places, you won't see any of the other messages. And sinc functions actually have that nice property. Okay, so with that as kind of the introduction to modulation here in the last 5 minutes, what I'd like to do is talk about the third item on my list, which is also in section 1.1 of the course reader. And that's what's called an inner product. And an inner product, almost everybody's seen dot products in your vector physics classes as undergraduate. But we're going to somewhat generalize that concept to a correlation, if you will, of two waveforms. You can write this a lot of ways. In the notes I've been using this format, which I sometimes also write, you see these brackets outside as U dot V. Okay to do that. Or the dot is kind of big, so for dot product. And what this is is the integral from minus infinity to plus infinity of u of t times v of t dt. Okay, now this integral is kind of like a sum of products. Now you remember from your basic physics class, if you took a couple of vectors and you took their inner product or their dot product, you take the first component of the two vectors, multiply them together, add it to the product of the second two components, and so on, up to the last components, take the products and add that together. Well, this integral is just doing that in continuous time. So you can look at it as being a dot product or an inner product. If you had two vectors instead, let's say u and v, so that these are both data symbols, if you will, then the inner product takes a form that looks very familiar, which is simply take the components and multiply them together. So this is how it's defined for vectors. This is how it's defined for functions. And if u dot v, whether they're vectors or functions, is equal to 0, then the functions or the vectors are said to be orthogonal. So remember the dot product, sometimes you take one vector's magnitude times the other vector's magnitude times the cosine of the angle between them. So if the 90 degrees and cosine 0, okay, so vectors that look like that are orthogonal to one another. Well, functions can look that way also. Those FDM functions we just talked about a second ago would have this particular property of being orthogonal, and that is a special instance of a theorem which is called the invariance of the inner product. If I can write u of t equal to sum from n equal 1 to n of u sub n phi n of t, where phi n are an orthonormal set of basis functions. And I can also write in terms of that same orthonormal basis Vn in this form. Then u dot v is equal to u of t v of t. There's an easy proof in the notes of that. So it may be easier to do that inner product. In fact, on homework set number 1, you'll find a number of cases where that will be a lot easier to recognize that you have an orthonormal set of basis functions and you'll be able to pull out the vector components and take the inner product that way, as opposed to doing the integral, which may have some nastiness in it in terms of being able to do it. Now, a specific example of this is if I let n go to infinity and turn these into integrals, and the phi n of t actually look like something like e to the j omega t, like you see in Fourier transforms. A version of this is that u of t, as long as both of these functions have a Fourier transform, u of f, e of f, which is sometimes called Parseval's theorem. Okay. As long as you can write it as a sum of orthogonal components, which is what those frequency components are for the Fourier transform. It's taking a time domain waveform and writing it in terms of a set of orthogonal components at each and every little frequency. Those are all orthogonal to one another. Then you can write, this is sometimes called Parseval's theorem, you would see. So this is something that you can use also. But of particular interest to us in modulation, because we're going to have finite number of basis functions, is this type of orthogonality. Now, a third example of this is kind of interesting. Suppose I define a vector, phi n, which is, I'm going to write it in its transpose here so I don't run out of room on the paper, but a bunch of zeros with a 1 in the nth position, and some more zeros. I'll put that prime there for transpose. I could do this, then xn, the nth component of the vector x, could be written as a vector x dotted with phi n. Now clearly I'm representing phi n here, okay? Phi of t can be represented, phi n of t can be represented in terms of a sum, which is all zeros except for picking it out of the basis set. So that's all that means. I found a vector representation for that particular function, the basis set. And if I know that x was a modulated waveform, okay, because I designed it that way, I could pick off its nth component by taking x dot phi sub n. That's trivial if I think of vectors, because I've got zeros, 0 times the first component, 0 times the second, all the way up to the nth component where I have 1, so I pick off x sub n, which is also, because of the invariance of the inner product, going to be x of t times phi n of t, which perhaps isn't so obvious when you look at that integral. And this last integral, okay, recognizing this, is basically going to be key to constructing a demodulator. What we're going to do in the receiver is basically have a functionality that is equivalent to this integral. And if I can do this in the analog domain somehow, the equivalent of this integral, I will get the nth component. If I do it for each and every one of the basis functions, I'll generate the data symbol. And then I look at the constellation and say what point, okay, what possible message point in the data constellation looks like the one that just came out of the channel. And I will have constructed then a demodulator in a formal sense for this modulation process that we defined here today. So we're right at time, so I'll encourage you to please go read section 1.1, and then we'll see everybody at 9:30 on Thursday.
Why do we have more than n components of the basis function if x only goes up to n? Or is this just the nth x and it can go? Oh.
You answered your own question?
I think so.
I didn't quite understand your question. But
I think I was confused that this is x could be like n plus 1 or n plus 2.
it could be any of
Okay.
the indices.
Oh, I was thinking of n in terms of the last.
No, that's capital N.
Yeah.